Hi everyone, today I wanted to talk about the history of the inner Milky Way as traced by variable stars. So one of the real challenges for understanding the formation and evolution of galactic bulges over cosmic time is understanding the sequence of events by which they formed. And in the Milky Way, we can get a very detailed idea of this sequence of events by studying the individual stars that make up these structures. And so one of the really important things that we want to know is exactly when the bar of the Milky Way formed. The bar is an important dynamical driver, reshaping the distributions of stars and gas within the galaxy, and knowing exactly how long it's been doing this is very important for the interpretation of other observations. However, it's a challenging measurement to make because the age of the bar does not equal the age of the stars within the bar. The stars within the bar likely formed in some precursor disk, or they could have been captured into the bar. And so the key then is to look at a structure that only started forming stars when the bar was formed. And that structure I'm going to focus on here is the nuclear stellar disk. The nuclear stellar disk is a highly flattened structure within the inner degree or so of the center of the Milky Way. It seems to be rotating and it's very vertically cold. As recently highlighted by Barbara and Kawata, the nuclear stellar disk likely formed when the bar formed and gas rapidly was funneled towards the center of the galaxy, settled into these central X2 orbits and began forming stars, which then become the nuclear stellar disk. So knowing the age of the oldest nuclear stellar disk object will give us the age of the bar. This is also the idea behind the MUSE timer survey. But it's a very challenging thing to do in the Milky Way because the central regions of the galaxy are very highly extincted, they're very highly crowded. So one option is to look at color magnitude diagrams and look at the distributions of the giant branch across different populations. However, for intermediate ages, the effects of changing the age are quite subtle on the giant branch. And so here I'm proposing using a different tracer, and that's Mira variable stars. So Mira variables, they're very bright, pulsating asymptotic giant branch stars with periods between 80 and 1,000 days. As I said, they're very bright and particularly bright in the infrared. So they're very useful for studying highly extincted regions. And it's been known for some time that their periods correlate with age. And this is mostly an empirical observation, mostly based on the looking at the dispersion as a function of period, where the lower, shorter period objects clearly have hotter kinematics that we'd associate with older ages. And this has been used quite recently in James Grady's work to understand the inside-out formation of the Milky Way using Mira variables from Gaia. However, the exact period-age relation is quite uncertain, and there needs to be some considerable work in understanding exactly the form of this relation. However, largely the empirical relations all agree with each other. I should also highlight that Miras are being used in the last few years as cosmological tracers because they satisfy quite tight period luminosity relations. And so to really understand how the properties of Mira variables vary with population, we want to form or have samples of Mira variables across different local populations that we can study well. And so those at the Galactic Center are an interesting set. And so how am I going to find these Mira variables? Well, I'm using the VVV survey, which is a near-infrared survey focused on the bulge and the southern disk. There are about 500 million light curves in the KS band, and then they're complemented by epochs of Z, Y, J, and H photometry. And we have observations over about a 10-year baseline. And I'm using the Virec version 2 reduction due to Lee Smith, which is a complete astrometric and photometric re-reduction using PSF photometry, and which allows us to go a magnitude deeper than the previous version. As you can see here, now in sort of low crowded regions, we go down to about magnitude 17 in K, whereas around the galactic center, it's more like 16th, 17th. And then also the reduction has proper motions measured because of the very long 10-year baseline, and these are anchored to the Gaia reference frame. And so compared to the previous iteration, we're now getting down to typical uncertainties for a star at the galactic center, a typical red clump giant at the galactic center. We're getting down to uncertainties of less than 10 kilometers a second in the proper motions. And so this is a great data set for measuring or understanding very cold populations. So this is the data set I'm working with, about 500 million light curves with proper motions. So I should highlight that recently, together with a master's student, Thomas Molnar, I ran a supervised classification of this full data set, and we found about 1.5 million variable stars for example, like Aura Lyrae, eclipsing binaries, some likely Cepheids. And this was a supervised learning algorithm based on pre-existing variable star data sets. And we're getting, for Aura Lyrae, we're getting upwards of like 95% reliability here. You can see, if we look at the Ogle distribution of Aura Lyrae, that we're getting much deeper into the plane compared to Ogle, because of observing in the KS band, we're able to go sort of much deeper through the dust. And using a visual classification or visual check, we found that the misclassification rate for the Aura Lyrae set was less than 1%, and its completeness is around 90% compared to Ogle. So this is a really interesting data set for now extending the samples of Aura Lyrae stars we have in the inner galaxy and trying to understand any kind of classical bulge component. And so very quickly and simply, we just looked at the distribution of Aura Lyrae here as a top-down view. And you can see that they clearly trace a barred structure centered on their galactic center, and they clearly seem to be rotating. And this aligns nicely with the conclusions from Hangji Du's paper from a couple of years ago using the Ogle Aura Lyrae dataset. And so going back to the MIRAs, the MIRA study was a much more focused study on just a very small region that contained the nuclear stellar disk, the inner 3 by 3 degrees. And I was guided by previous work from Noriyuki Matsunaga, who extracted a sample of likely MIRA variable stars. And you can see most of them, or nearly all of them, have KS interquartile range greater than 0.1 here. So that was used as an initial cut to generate a sample of stars that were worth looking at as likely MIRA candidates. Then for each of these stars, I ran some light curve modeling using quite flexible Gaussian process models that allowed for peak-to-peak variation in the light curves, which you sometimes get with MIRAs or high amplitude semi-regular variable stars. And then also you get small shifts in the periods which the Gaussian process accommodates. And so here's some examples, one that's very well sampled, one that's quite poorly sampled, but in most cases, we're getting a very good recovery of the period for these MIRAs. I also ran some multi-band light curve modeling, including the other epochs, the ZYJH from VVV, sometimes the Matsunaga data when available, and also the WISE data, which has quite a poor cadence of almost exactly 6 months, which isn't great for studying these kind of objects, but allows us sometimes to refine the periods that we're getting just from a single band analysis. And so then if we plot up the periods versus K-band amplitude, you can quite clearly see a sequence that sits on top of this, this kind of background of lower amplitude objects, which are likely semi-regular variables. This sequence is the MIRA variable sequence, and this is sort of confirmed by comparison with the sample from Matsunaga, which clearly sit within this box, periods between 80 and 1,000 days, and this kind of flat amplitude until about 400 days, and then it begins rising. So we select MIRAs in that box, remove some likely young stellar object contaminants, and this leaves us with about 1,800 MIRA variables, which all have proper motion data. So are these nuclear stellar disk objects? Well, if we plot their distribution on the sky, you can see it's highly flattened, and this agrees nicely with the distribution of the AGB bump stars, as you can see by the black contours on the left. Their distances are also fairly consistent with galactic center location, although they could be bar bulge contaminants. But the distribution that we see on the sky is actually quite affected by the completeness. We really miss bright objects in VVV because they're just too saturated. Below about a magnitude of 11, saturation effects begin kicking in. By about magnitude 10, we just don't see, we just don't get any reliable detections of these objects. And so we're really missing the bright objects here. So we only see objects in the high extinction regions. And that's why we see a very flattened structure on the sky. So coming back to the main point of this talk, what do the periods and age distribution look like? Well, the period distribution is here shown on the right, where you can see, as compared to the LMC and galactic bulge populations, we have a very young wing, a sort of a high long period wing, and also a short period old age wing. And when we map into age space using these approximate period age relations, you can see that the age distribution is relatively flat. We get sort of recent signs of recent star formation, signs of very old populations, and then there's a suggestion of a dip here at about 8 billion years ago. But the real problem with this kind of very basic analysis is we just don't really know exactly which stars are members of the nuclear stellar disk and which are just bar bulge interlopers that just happen to be in that location as they're sort of passing through the nuclear stellar disk region. And so that's why the kinematics are so important. So we have two components of the proper motion, the sort of in-plane proper motion and the vertical out-of-plane proper motion. And in the mean, both show kinematics consistent with location at the galactic center. So they have means consistent with the proper motion of Sagittarius A star. And you can see here on the right that there is a very cold component to the kinematics. Also, if we just select stars that are have long periods, so longer than 400 days, you can clearly see a double peak structure in the in-plane proper motions, which is probably a signature of the rotation of the population that we're seeing both the front and the back side of the nuclear stellar disk. And we just don't see that in the shorter period stars, possibly because there's bar bulge contaminants, or possibly just because they're a hotter population. And so I've run a couple of simple analyses to try and measure from the kinematics the relative contributions of the nuclear stellar disk and the bar bulge. The first is using a very simple Gaussian mixture model. And on the right, this is the dispersion for one of the components. And you can see how at high periods, so young ages, the dispersion is very low, sort of around or below 30 kilometers a second. But below periods about 250 days, which correspond to about 8 billion years ago, the dispersion begins rising, and up at about 150 days, we have dispersions that are consistent with the surrounding bulge. And so this then gives very clear evidence that there was there's some difference in the populations above and below 8 billion years. Another analysis is using the dynamical model from Matthias Sormani's recent nuclear stellar disk work that was fitting spectroscopic and proper motion data, and trying to find how much of that component is needed and how much of a bulge component is needed, where the bulge component has been measured from the surrounding high latitude observations. And so here you can see various proper motion distributions sorted by period. So period is increasing as we go to the right, so age is decreasing. And you see in the low period bins essentially no evidence of a nuclear stellar disk component. But as we go between about, as we go beyond about 8 billion years, we have a significant nuclear stellar disk component. And so this is very consistent with the idea that there's bulge before 8 billion years ago, and then the nuclear stellar disk begins forming 8 billion years ago. So the bar likely formed at that epoch. So that's all I'd like to say. So what does this tell us about the formation and evolution of galactic bulges? Well, as I tried to motivate early on, dating exactly when the Milky Way bar formed is very important for understanding the dynamical history of the entire galaxy. And looking at the nuclear stellar disk and its star formation history tells us something about exactly when the bar formed. I've presented evidence from the proper motions of Mira variable stars that there's essentially no nuclear stellar disk component for stars older than 8 billion years ago. So this gives strong evidence that the bar formed about 8 billion years ago. And this could have coincided with the accretion of the Gaia sausage Enceladus galaxy.